All right, let's talk about caching finally. So did I put this in the right folder? It looks like I did. Good. So some cool things to talk about. We're going to learn how caching works and why it's a thing. There's a section of your book or a chapter of your book about it, so please read chapter 11 of your Dive into Systems textbook. That will go over this kind of stuff and give you a more solid foundation on it. All right, just in case I forget to say something. So let's talk about the caching hierarchy, because you remember that there was a memory hierarchy, right? And it looked like this. It was a triangle. There were registers at the top. Those are the smallest, most expensive things, but they were super quick to read. Then there was this magical thing called the cache, which we didn't really explain much yet. That's what we're doing today. And then beneath that was your main memory, which is cheaper than registers and caches, but can hold more things, but it's farther away from the CPU, and so it's like it takes more time to read, and we wish that we didn't have to go to main memory all the time. And then beneath that you have your secondary memory. Like your hard drive takes even longer to read stuff out of there. So that's why everything, when we run a program, first of all, it's being copied off of your hard drive into your RAM so that it can at least be somewhat fast. That's the goal, at least. So we're going to zoom in on this little pillar right here, because there's actually a hierarchy of caches too. So there's stuff inside of this. Like boop boop. There's things to look into. All right, so let's break that down even more. So here's the goal of caching. All right, so let's pretend. Take a minute to pretend in a silly way that you're a computer right now, and like the CPU is your brain, and like where is all of the information that could ever be like retrieved for you? Let's say that it's in some giant library. Like the biggest library ever is probably like the Library of Congress, let's say. So that's the example that your book is saying. So like your brain is pretty far away from Washington D.C. right now, and it takes a while to walk through the aisles anyway, even if you live in D.C., to like go and find the book that you're looking for and like get the like the data that you need. Okay, so the idea of a cache is to have things closer to you so that you can access them more quickly. Okay, so they're like your local library. That's much faster and quicker to access than the Library of Congress, though the Library of Congress has more stuff. Okay, and then you also have like the shelf in front of you in your room. That's only a few steps away, and it's not a drive to the library, but you can't fit as many things, right? There's a hierarchy going. There's a hierarchy brewing, isn't there? And then like the desk, you can only fit so many books on your desk, especially my desk that's very, very dirty and does not have a lot of room right now. So again, it's immediately accessible, maybe your desk, but you can't hold as many things. And that is all the same idea again. There's another triangle, okay? So like your desk is faster to access, but the capacity is smaller, okay? Like your books can, all the data you need at your desk you can look at right now, but you can only hold so many things. If you need stuff for later that you might want later, you put it on your shelf, and like you can go and like look through your giant library in your room and find something within a minute, let's say, and then like your local library, you can go take a short drive and go walk through the aisles and get something within like 15 minutes, let's say. And like even lower than that is the Library of Congress. You got to go fly to DC if you want something that's very niche and is only located there. Okay, so this translates pretty much exactly to this kind of picture all over again. So registers, they're small, they're quick to access, less than a nanosecond these days. They can only hold so much, like 8 bytes for an X register, 4 bytes for a W register. The cache inside of the CPU is something new that we're about to talk about. It can hold a few megabytes of information, but it takes a few clock cycles to access, 5 nanoseconds or so, to get something out of the cache. But that's way better than going to disk or going to main memory even. So main memory, to get something out of there, like people have 64 gigs of RAM these days, but it takes a while. It takes hundreds of clock cycles to go and look at memory and get something back from it. So the CPU is wasting time. So wouldn't it be nice if we had stuff in registers? And if not in registers, let's put it in the cache. All right, that's the new place. So the cache was built with the idea of locality in mind. So there are 2 kinds of locality that often happen in programs, and the idea of a cache is let's take advantage of locality. All right. So there's 2 main kinds of locality. So the first is called temporal locality. This is when, like, when you have a program, you usually are going to access the same data repeatedly over time, aren't you? Okay, so like when you have a loop for int I equals 0, I is less than whatever I plus plus, and if I is in memory, right, I is something that you care about, wherever, could be in register, could be somewhere special, you have I in your program in assembly somewhere, right? And you're accessing I over and over and over again. So the solution to exploit temporal locality, like you're going to keep accessing the I over and over and over again, the best course of action for I is like don't put it on the stack in main memory, put it in a register or something, because you're going to keep accessing it, right? Save memory that you recently accessed close to the ALU. And if you don't have enough room in a register, we're going to place it in the cache, because that's still closer to the ALU than main memory, right? Where the like addition on I would take place. Okay? I hope that makes sense. So that's temporal locality, and this is its solution. Save things that you're going to keep accessing closer to the ALU. Closer, as close as you can. Not even in memory. Closer than main memory, all right? The other kind of locality is called spatial locality. And this is an interesting one. It's when programs that you write, usually when they access data, they're not just going to access data at that particular address, they're also going to access data at a nearby address, okay? Close to something that you've previously accessed. So this is very common, and you see this a lot when you are using, you're messing with, like you're going into R of I or something in your loop, and you're adding it into a sum variable or doing something, but you're messing with the next place in I each time, all right? So because of that, because you're never going to go back to exactly R of I again, it's a good idea when you access an address, when you go to address X in your code, in your assembly, let's say, and you save its data for later, don't just cache that particular address. So cache is a verb as well. Don't just save that particular address in your cache. Also, you should save things close by address X. Save like X minus 8 address, X minus 4, X plus 4, X plus 8, X plus 12, because you're probably going to go there too, right? You might be going backwards, you might be going forwards, you're not sure, but save them all because you might be coming at them soon. Get them closer to the CPU than the main memory. Put them in this thing called the cache, okay? And so they're all going to go in a special place. You're not going to read just one thing into your cache. You're going to read a whole block of things into your cache, and we call that a cache block. All right? So whenever you read address X, here's what we'd like to have happen. We'd like to save all this X itself, of course, closer to the CPU, as well as all the stuff nearby address X. So all of these things go in a cache block, we say. All right? And that is the goal. Then it's closer to the CPU, so that when you go to this place next time, X plus 4 or whatever, if it's a bunch of ints, it's already sitting in the cache, and you don't ever have to look at memory again. So you've saved a lot of time. All right, so that's spatial locality and how you take advantage of it. So the cache is the answer to both of these, by the way. And there are a few of them. There's a hierarchy of caches, okay? And so you remember this picture from multi-core machines. There's a few different levels of caches, and some of those caches live on the CPU itself, baby tiny caches. And then there's also some shared caches that every core gets to use together. All right, that's a bit longer, that's a bit bigger. And the levels of caches are abbreviated like this. You got like, these days there's like 3 levels usually. You got an L1 cache, which is living in each core. And I'm pretty sure L2 also lives in each core. And then L3 is the shared, for sure. It's the shared cache memory. And so you might have heard these terms before if you ever like bought a CPU and built stuff, okay? So the goal of caching is, all right, I read an address out of RAM, like for the first time. If I go to address 12 or something, I've never been there before, I'm forced to go to main memory because that's where it's living, all right? But then the second I read it, I am caching it. I'm caching a whole block, right? A whole cache block. If I try to go here, I'm saving an entire cache block. So that thing, the address that I just read, I'm taking a whole block of information around that, saving it on the cache. And let's say it was core 1, that was the CPU core that was actually asking for that memory. I'm going to store it in its also smaller cache. And so now I've duplicated this thing from memory to other places that are closer to the ALU where I'll need them, and now they're faster to access. So that address, the values of that address, I've read them and I've saved them for later in the cache. So hopefully the next time I look for something, it'll be here again in this closest cache, L1 cache or L2 cache. But maybe I've read other things, and like I've gotten rid of that somehow from this cache. I can then go and look in this one still, and it might still be there, okay? Because that one has more space for things. So that's what's kind of happening. It'll take some more pictures to fully have it sink in, but that is the high-level idea of caching. Right? There's a hierarchy to it. Right? So there's multiple ones. So we'd like to avoid hitting main memory at all potential costs. So we have multiple levels of caches, and they're getting bigger each time. Right? So this triangle is almost to scale. Okay? They're getting bigger each time. The first cache is the smallest one. It's your level 1 cache, L1 cache. It's very small and very fast. It's as close to the ALU as possible. It's as close as you can be that isn't just a register anymore. All right, so that's the L1 cache. So like here's the actual like registers, and here's the ALU and all that, the pants, right? That's the drawing. The L1 cache is like the closest place you can get to registers. You'll have to read it into a register eventually, right? But that's the L1 cache, very close. If you can't find what you're looking for in the L1 cache, hopefully it's in the L2 cache, level 2 cache. It's slightly larger and slightly farther away, so it's slower to access. But it's still better than going to main memory. So it's a little bit bigger, L2. This is not quite to scale, but it's a little bit bigger, right, than the L1 cache. So if you lost something out of L1, it got clobbered away. It might still be in L2. And if it's not there, you can go looking in the L3 cache, which you're saving stuff. Every time you read something, it's going in the L3 cache as well, which is even bigger, which is shared. That's a shared cache away. Multi-core machines have an L3 cache that's shared between cores. Larger, slower, still closer than main memory though. And if that thing, right, still light years faster than reading main memory from L3, if finally that thing you can't get, it's not there in L3 either, you got to go to your giant main memory and wait a while to read it for the first time. Alright, and then you can get it into the register finally that you wanted to. So yeah, this is kind of the hierarchy, and this is the goal. If you can't find the thing you're looking for in the L1 cache, it might be in L2 because it had more memory. It didn't get clobbered there maybe. If you can't find it in L2, maybe it's in the L3 cache. Only in the rare case where you haven't ever seen this address before, you haven't ever seen anything around it before, do you need to go to main memory, and then what happens when you read from main memory are these arrows are kind of what you want. You have a load instruction, right? The whole idea is that you have a load instruction. Load into, I don't know, W0 from X1 or whatever. Like, this is why you're going to memory. And say you've never seen this address before, you will have to go to main memory, but you are copying an entire cache block from this address onwards. You're taking the whole thing. Once you read from main memory, you're copying it into the L3 cache, the L2 cache, the L1 cache, and then you're also putting it in the register all at the same time, so that you've saved that block in a bunch of different places. Okay? That's how caching works. All right? Sometimes you're clobbering old stuff, like in L1, because you don't have a lot of room, but hopefully the stuff from before that got clobbered has been kept around in the bigger caches. Okay? So that's what hierarchical caching is all about. All right? So here are some terms involved. Let's pretend, again, we got like a load instruction. Pretend we're loading an address from memory. We got our load instruction, load into W1 from X0 this time. Who knows? Something like that. So when you're loading something, you're going to go look in your cache first. All right? When you go and you look in your cache and you find it there, it's called a cache hit. All right? It's called a cache hit. Do I want to say anything special right now? I think I do. Just even before we get into this example, there's actually two kinds of caching. There's two kinds of L1 caches, which this instruction or this diagram shows more accurately. This is like the most accurate version of the cache hierarchy these days. There's actually two separate L1 caches. There's one just for data in your data section, and then there's also a separate cache for instructions, because also instructions are being loaded out of memory, right? And you want those close. You want to read a chunk of them because you're probably going to read the one right after the one you're currently executing, right? So there's a cache for instructions as well as for data. So let's say we're trying to read some data. So we're going to go look in our L1 data cache first. If it's not there, we'll look in our L2 cache, right? If we find something in a cache, it's called a cache hit. If we don't find it in a cache, that address wasn't there, it's called a cache miss. So if we missed it out of L1, then we'll go see if we can find it in L2. If it's there, it's a hit, we'll bring it back in, okay? If it wasn't there, we'll go to our L3 cache. Hopefully it's there, okay? And then we'll find it if it might hit the L3 cache. And then if we can't find it, then we have to go all the way to memory. That's our DRAM. And then the second we can't find something somewhere, we're always going to copy it back. Like if we're going to go read that address, a whole cache block of stuff into the L1 or the L3 cache, also copy it into the L2 cache, and then also copy it into the L1 data cache if it's data. All right. So that's how that works. On a miss, if you have a cache miss, you go all the way to main memory, copy it all into every hierarchy of caches, and hopefully it'll stick around for a while in at least one of them. Okay? So that's the idea. So that is some new terminology. And yeah, let me prove to you that missing the cache makes things really slow. So let's use this program from the right because it's part of your book. I also have this program that I made. Sorry, the right example. I made the right example. You can zoom in and copy it out of here if you want to. It's pretty cool if you've seen CSCI 26 information. But here's an example from your book. We'll just copy and paste it. It proves that the cache is important. We'll time our program. All right, we'll time this fancy program. It is a C program, and so I'll paste it in here. Boop. So what this is doing, there it goes, it is a program that creates a big long array. I think it's a two-dimensional array. Yeah, it's making a giant two-dimensional array. All right, crazy, which it's calling a matrix. All right, so we're supposed to give it a number, whereas like that's the dimension of our matrix. It's a something by something matrix, like 100 by something by 100 matrix maybe. So what it's going to do is it's going to generate a random matrix of values, a two-dimensional array essentially, and then we have two versions that get the average value out of our giant array, right? Two versions. Let's see, how do I want to do this? Average V1, yeah. So we've made an n by n two-dimensional array, which you can read out like this. Here is average matrix V1. It's reading, it's like it's going to every index of the matrix, and it's summing them all up, and it's taking the average value. All right, so that's one way to write the average, given a two-dimensional array of ints. Another way to do that and get the average value of a two-dimensional array of ints is this way, which is still going to hit everybody, but now instead of adding in matrix ij plus equals matrix ij, we're going to plus equals matrix ji. It's different. That's the only difference between these two versions of the average function. Okay, they're going to read the same stuff, but they're going to read the stuff in different orders. All right, so you can kind of see where we're going with this in terms of locality. Yeah. So it's reading two different things. This one's reading in this way, this one's reading in this way. And that's the only difference. Like this program just makes a giant random matrix of a certain size, an n by n matrix where we give the n value. And it's calculating and timing how long it takes to run the first version to get the average and how long it takes to get the second average using the second version. Same matrix though. Same two-dimensional array. So let's compile and run this. Oops, I added a dot. Let's compile it without that dot. So if I say I gotta run it with a number, so like 100 by 100 matrix, it's still pretty fast. Those are both very fast. It finds the same answer, of course. But if I did like a million, or maybe 100,000 by 100,000 matrix, perfect. Whee, so this will take a while. Maybe this is too big. Yeah, let's kill that. Let's do 10,000 by 10,000 matrix. There we go. So the first one, to calculate the average, it took less than half a second even to do it. That part was fast. So the V1 version of the average was fast. But the V2 version, it's doing the same code. It's still, these are both what, they're essentially linear time algorithms because it's a two-dimensional array, right? But it's visiting every index one, so it's linear in the number of elements in this two-dimensional array. So they're the same running time complexity. They're both linear, but just swapping these orders and visiting these elements in a different way for V2 makes it over double as fast, or double as slow, excuse me. It's several times slower. It's 10 times slower. Do you see that? And that's because we're having cache misses happen. The way that this is working, matrix ij, that's a normal way to read from a, let's see. from an array. Here's what it's doing, kind of. We're generating this giant two-dimensional array, which looks like this. And to read in the order that we're reading, like let's say I have a 3x3 array. To read in this way, the i's are controlling, usually that's like your row and the j's are your columns. So this is I equals 0, j equals 0. In the first version, what it's doing is it's reading this one, and then it's going to read this one after that, which is right next to it in memory, right? And then it's going to read this one after that. And then it has to kind of jump over that. This is in a different place in memory, but these guys were all kind of close to each other. And so as we read in a cache line, our temporal locality, or our spatial locality, put all those together, and we were hitting the cache along this entire row of the matrix, all right? And then you go to this one, read that one, read that one, read that one. That's how the first one is reading its values. The other one, version 2, is doing it out of order. It's doing JI. So, still, it's arranged in memory in the same way. Here's how it's reading its values. It's going JI. So it's reading index 0, 0 first still. So this is I. This is j equals 0. And then it's doing j equals 1, I equals 0 next. So it's jumping across to here, which is a completely different place in memory. See that? This is not in the same cache block. And then it jumps to this one, right? And then you can imagine that it's going to jump back up here in the next iteration of the outer loop. So it is missing the cache every time it reads a value with a big enough array. And size 10,000 is missing the cache every time it reads a value. So we're getting stuff out of there. It's never there. It's never ever there. And so it's 10 times slower, even though it's the same complexity, same running time complexity of the program. We're just reading things in a weirder way. Isn't that disgusting? So if you think about it in terms of n, because we're giving n, where n's the size of the matrix, it's making an n by n matrix, and we're visiting all of the n squared things. So it's an n squared algorithm, both of these guys, if you think about it like that. But oh man, this one's 10 times slower if you just read it in a way that the cache does not like, because you've missed it every time. This is a bunch of cache hits. This is a bunch of cache misses. Computes the same answer, same running time complexity. That's disgusting, isn't it? So you have to think about the cache now when you're writing your programs. All right, keep track of write programs that exhibit good locality. Okay, so let's talk about the different kinds of caches now. All right, there's a direct mapped cache. That's the easiest one to explain. So I'll teach that one first. So when you've got a direct mapped cache, what it's doing is it's kind of chunking up the main memory into different things that are the same width as what the cache is going to read into each, like the size of each cache block. All right, so those are called cache lines. So here's like our main memory with all of its addresses, and then here's our direct mapped cache example. It's capable of holding 4 different cache lines at once, and each line can store a block, a cache block. Okay, that's the goal. And every cache line, usually these days, holds some number of bytes. So it's like 16 to 64 bytes. In this particular example, it looks like the red space is hexadecimal 20 worth of addresses. So it's, I guess, 32 bytes per cache block now. So that's kind of how that works. And so you can kind of see from the picture what's going to happen. If you try to read an address from here, it's going to go and look in the red cache block. Same with this one. It's going to go and look in the red cache block, and they're kind of fighting for that line, okay? They're all going to be mapped to there. I hope that makes sense. And so when you go, like, let's say your program wants to read address, I don't know, 0x1c or something. Here's kind of how that works in a direct mapped cache. The line of the cache that you're going to check, you kind of calculate it like this. You're going to divide your address by the block size, which is apparently 32 bytes in this example. So that was 0x1c divided by 32, integer division land. So that's 0. And then you do mod number of lines you have. And so 0 mod 4 is still 0. So it's going to go and look here. It's going to be like, okay, this, hopefully it's there. I'll go look at it in this part of the cache block on line 0. And hopefully that's what's been stored there. Okay. But you have other people fighting for that as well. So like this is, I don't know, if you try to read from address 2F, right, it's going to go and look over here in line 1, because you're just going to calculate like this. All right, address 2F, divide by the size of each cache block, so that's 1 mod the number of lines I have, so that's going to go look in line 1 for what I see there. Hopefully it's there, okay? Everybody who's colored red, though, all these things are going to be like fighting for each other. So like if I try to read something like an 80 something, 8 something address, then oh no, it's gonna clobber things. If I go and try to read from address 80 and it's not in the cache block, because like it's this line, it's addresses it's holding right now, addresses 00 to 1F, that's in the cache line right now. If I try to read this one, it's gonna clobber the old one, all right? Because it's gonna go like, if I try to read, what is this? Let's say this is address 86 or something. So again, I'm trying to go 0x86 divided by 32, and then mod 4 to figure out which block is it going to go to. Sorry, which line is it going to go to? It's going to line 0 again. And it's going to clobber the old one, and we're going to save it there in the cache if it wasn't there already. Okay, that's kind of how that works. So I hope that makes sense. There's a little bit of sense. And so the cache kind of has to remember, like, it's going to read a bunch at a time into this block. So if you read address this thing, it's going to take all of the red stuff and shove it in there for temporal locality reasons, right? And it'll also remember like which chunk of stuff is actually in line 0 right now. It needs to remember like, oh, I'm holding 80 through 9F rather than 00 through 1F. Okay. So yeah, each cache line could hold many different memory regions, so it has some metadata about where does this line start. It's like, all right, it used to be starting at 0x0000, but now it's starting at address 0080. So like that's the metadata that it's keeping track of, okay? That's the idea. So it's reading a whole chunk at once, reading a whole block at once. That's how you think of a direct mapped cache, right? So here's an example. Let's do it ourselves. Let's pretend we have a direct mapped cache with 8 lines, all right? And let's pretend that our block size is 16 bytes, all right? 16 bytes. Every time we read something, we're getting 16 bytes of data. That's how big our blocks are, all right? So let's say that our program wants to read these addresses in this order. Doesn't matter how much it wants to read. It wants to read from these addresses in this order. Let's figure out like which line it's going to try to read from. See if it's there or not, see if we hit or missed, right? And we'll figure out like how it all works, and we'll learn some new terms along the way, all right? So let's say we want to read from address FA first, all right? So again, the line that we want to check is our address FA divided by the number of things in our block, bytes in our block, so by 16, and then we're going to do mod number of lines in our direct mapped cache. So we got 8, so mod 8. And if you think about it, the answer is 7. It's trying to go to this one. And it's not going to find it there. But if you think about it, this is, well, first of all, this is a hexadecimal number. If you do divided by 16 integer division, you can just, the equivalent of that is right shift by 4, right? So you just kind of chopped off this lowest hex digit. So now it's just 0xf, and it's this in binary. And then if you want to do mod 8, it's really just like look at the last 3 bits, right? Because you're modding away everything bigger than that, every other multiple of 8. So just look at the last 3 bits of after you shift right by 4. So honestly, the line to check for your cache, right? Which line do you check if you're trying to read address FA? Just look at bits 7 through 5. That's all you're doing. So when you're implementing a cache, if you become a computer engineer and you make your own cache one day, it's not actually doing division or remainder to look for like which line should this thing be in. It's just looking at bits. That's all it's doing, right? So yeah, if we try to read from FA, we're going to go here to line 7, right? Just like we noticed, and we're not going to find the value there. So there's nothing in the cache right now. Pretend that it's empty. We just turned the computer on, and so we missed the cache, sadly. We missed the cache. It wasn't in there, but we're going to store 16 bytes of stuff there from F0 to FF. That's going to be placed in the cache now. So if you try to read FA again, or like FB even, it's going to be there. The stuff at those addresses will be there. All right? So that's the goal of a cache. Let's do the next one. So we're going to try to read address 37 and see if it's in the cache already. It'll definitely miss, though, won't it? So we're going to do that same calculation. Those bits 5 through 7, if you wanted to look at it that way. 37, that's going to go to line 3. All right, line 3, it misses. Nothing's there right now, so it's going to load it in. So 30 through 3F will be held in the line 3 of our direct mapped cache that holds 8 lines total. All right. And yeah, if you keep playing this game, I think you can kind of see the game now. You load 4B, it's going to miss again. It should have gone here to line 4. And so we'll load in, save it for later, 40 through 4F. If we ever try to read any of those addresses, it is saved in our direct mapped cache now, right? And now we start having some hits. So like FA, we try to read FA. We go look it up in line 7. Hey, it's in the cache already. FA, that address has been saved previously. Thank you, temporal locality. Or was it spatial locality? Dun, dun, dun. Thank you, spatial locality. Cool. So it's there now. We found it. And so it was very quick to access this one when we read it this time. Same with 4C. It's being saved in line 4. We go look at it there and notice that, hey, it's good to go. Let's take it. All right. Next comes 7B. That's going to go, that's a miss. It would have been in line 7 if it was there, but it's not. We're holding something else there. And so what you do when you try to read something and the cache has something there already is we replace. If we miss on a non-empty cache, we have to replace the thing there with what we just read for temporal locality reasons, because you might come back there again. We're going to evict what was there already. We're mean old landlords, and we're getting rid of what was there before, and we're going to store in the most recent thing, so 7B. So 70 through 7F. All right? Because the hope is, with temporal locality, you're going to read a 7 something rather than an F something again, okay? And then BA, that's going to miss. That's not in our cache right now. Which line would it have gone to, though? BA. That would have gone to line 3. So, oh no, we have to evict these guys out. Store B0 through BF for next time. Hopefully it's there. And then 13B, one last time, that's going to be, I think, 3 again. And so, oh no, we missed. Yeah, that would be line 3. We go looking for it there. We don't see it, and so we're going to load it there. Hopefully somebody's going to go looking for that address again later. So this is now 130 through 13F stored in line 3 of the cache. Okay, so that's how a direct mapped cache works. Every time you load something and it misses, it's going to shove it into the cache on that line and evict somebody who was already there previously. Because the hope is that you're going to read the most recent thing next. Okay, not the old one that you evicted. All right, your turn. You try. So here's an example. It's going to be similar to a homework that I'm going to give you one day. Not today, though. Assume that you have a direct map cache with 8 lines, and each line is only capable of holding 1 byte. All right, so it makes your calculations very easy. You just do like divide by 1 mod 8, so it's just mod 8 this time. So just pretend you're only caching 1 address in each line, 1 byte value. And these are the addresses that our program wants to read in this order. And these are decimal addresses, not hex addresses. All right. So it wants to load these values into an empty cache to start. Let me do the first 4 for you, and then I want you to see what's there. Right. Keep track of any misses if you can. Think about it that way. So I'll do the first 4, then you do the rest. So 12. We want to read address 12, and each cache blocks are only 1 byte big in this example. So the line that address 12 will be in is 12 over 1 mod 8, so just 12 mod 8, which is 4, right? Then go looking for it. It's going to miss because it's not there, but it's going to place it there for next time, right? Then 17 mod 8 is 1, so it'll miss and place it here, all right? 3 mod 8 is still 3, it'll miss and place it here, okay? And then the last one, 12, then that's a hit. You see that? It's already there. We're going to look in line 4. We see it there. It's a hit. All right? You do the rest, please. So we're simulating a direct mapped cache. All right. So the 5 is going to go to 5 here. Cool. The 1 is going to go to line 1, but you can only hold 1 byte of data there, and 17 is what's being held right now. So the 1 has got to evict the 17. Now it's just 1 there. 13, 8, 9, 10, 11, 12, 13, that's 5. And so we're evicting the 5, sadly, holding 13. But that's good because we're reading 13 again right there. And so we hit the cache on that time. 4 is not there. It would have gone on line 4. We got 12 right there, so we're going to evict it, sadly. And then if we go back to read 12, oh no, it's been evicted. We have 4 there. So we're going to evict the 4 and put the 12 back. So that's kind of what's going to go on. All right, so that's a direct mapped cache. And you kind of see that there's some churn going on. Like these 12s and 4s, if we could just hold two things, right? Two separate chunks of cache blocks on line 4, I wouldn't have had to deal with this, right? We wouldn't have had to like miss the cache twice. So that leads to the next kind of cache, in fact. So yell at me if you have any questions about direct mapped, but you can kind of see how we might be able to improve caches if we were to save multiple things at each line, all right? So it's no fun evicting things every time there's a miss. Let's find a nice middle ground between like evicting everybody always and evicting nobody ever, all right? This is called set associative caching, all right? So if you have a set associative cache, it has mapped memory into different sets, all right? Every memory region maps into a particular set, just like for direct mapped, but each set is capable of holding multiple lines, okay? And you'll just evict like the oldest thing there or something. So inside of each set, you can keep multiple cache lines that would have collided were this a direct mapped cache, all right? So this is the idea. Like you're looking in the set and then you're just like looking, all right, the set brought me to one of these. Is my address in any of these? That's what you're gonna do, all right? So the set that you're gonna look for is address over block size again, mod number of sets this time, okay? So that's the idea. So if you do mod 6 or divide by 16 mod 3 and like it takes you to set number 3, then you go looking, right? If your calculation takes you here from the address you're trying to read from, you can look in here or in here to find what you're looking for. It might be in any of them. So you have options now. You're not always going to evict something if it wasn't there. You have two places where it could be as well. So that's pretty nice, all right? There's an overkill version of this, which nobody ever does, but like if you made just like everybody one set, then like every line could have gone anywhere. That's called a fully associative cache, and I'll show you that too. But this is a two-way set associative cache with 8 lines total, split up between sets, all right? 4 different sets. So I'll give you some examples of that. And first, though, we have to talk about, all right, we have 2 options now when we read an address, and if it wasn't in any of them, then we have to like kick out somebody, and so we have to figure out who to kick out now because we have options. So which of the lines in our set should we replace on a cache miss? What should happen? Well, there are 2 versions. There's the least recently used strategy, which is always going to be the best one for temporal locality, right? Which means replace the line that you accessed the longest time ago, because that one's probably not going to be read again. The most recent one's probably going to be the one that needs to stick around, right? That's always best for temporal locality, but it's hard to program because you have to add more metadata. Like you got to save the time that each of these lines were filled in for each set. And so a lot of CPUs nowadays, they just like randomly kick somebody out. They replace a random line in the set, which is like an approximation essentially of least recently used. It's never perfect, but it's easier to program inside of the CPU. So let's pretend we're doing the cool way though. We'll do LRU replacement. So here's my next example. Let's say that we've got a 2-way set associative cache. We're using LRU replacement. We've got 8 lines total, all right? And so we want to read these addresses again in that exact order. And here's our block size, 16 bytes. And we're checking sets, right? It's now sets to check. So we're going to do our address divided by 16 mod 4, okay? Mod 4 this time to see where it's going to be placed. And it can go in any of these lines once we figure out which set it's belonging to, okay? So back to my handy dandy calculator. We want to read FA, so we're going to do FA divided by 16 integer division land, mod 4 this time. All right, so that's going to be 3. So we go to set 3, and we could, we're missing because it's in neither of these, but we're going to go and look and see like, hey, is the thing I'm looking for anywhere here? If it's not, we want to evict the least recently used one. Let's just pretend it was 0 because like they're both empty right now. So I'll store my FA. It's really a cache line. It's like F0 through FF. It's going here. All right. And then I read 3.7. All right. 3.7. Which set is that going to go for? This will show us the beauty of the set associative cache. So this is also going to go and try and hit line 3. So with a direct map, or set 3, With a direct mapped cache, I would have had to evict this block, wouldn't I? But now I have more room. I have more room for my 3-7 and its entire line. It can go over here. Does that make sense? That's really nice. That's really, really nice, right? Remember, it's an entire block, though. It's 3-0 through 3F. I'm just being lazy right now. So then we read 4B. So again, we're going to figure out which block does that belong to. It's just going to be, I think it's block 0, right? Yeah. Block 0 is 4B. That's where that goes. We'll just put it here. We got room. It's going to be a miss, though. And then we read FA. With a direct map cache, we would have missed right here. But with a set associative cache, we're going to go to set 3 and then just look at both of these. Like, is my FA in one of these lines? Yes, it is. It's here. So we hit. Isn't that beautiful? We hit there. We see 4C, and that's going to hit this line. We're going to go to set 0, and it's like, oh yeah, it's in. We're going to look at both of these. We're going to see, okay, it's in line 0. It's there because it's holding 4-0 through 4F, the entire line, right? The whole block. Isn't that nice? Fewer misses this way. Then we have 7B. 7B, where's that going to go? I think that's 3 again, right? It's going to go to line 3, and oh no. Okay, so now we're going to set 3, looking for 7B in both of these. That line is not there, or that block is not there. So we have to evict somebody. And the goal is we have to evict one of these guys, the least recently used one. So we scroll backward in time. It looks like FA, that block, was used the most recently. So I'm going to evict 3-7, and that's where I'll place my 7B, right? And so that's trying to give you the best of all your worlds, because hopefully you'll come back for an F rather than a 3. And then 7B is in there now. Now we do BA. BA. And these are the same as before, right? These are all the same as before. You can see like all the evictions that happened with direct mapped, and there's fewer happening with set associative, with two-way set associative. All right, so BA is also going to 3, and so we're evicting the least recently used one. We just did 7B, so it's FA is least recently used, so that means BA goes in this line, and then 13B, 13B, is also going to line 3, isn't it? Set 3. So again, we're looking here, like, is it there? No, we're missing, and so we have to evict somebody. We'll evict the least recently used one. We just did the BA, so 7B is the older one. We're going to evict that and place in the line 13B, so it's really 130 through 13F. And do you see how we had to do 3 evictions here, and I guess this is a bad example because we also had to do 3 evictions here, but you can imagine that as you read more things more often, you're going to get more hits, okay? That is why it is good and useful. So yeah, your turn. Let's pretend that we're just holding a single address this time. Not every cache block is just 1 byte wide, but still two-way set associative with LRU replacement, and we're going to load these same addresses, all right? These same addresses from the last one. So hopefully we'll see fewer evictions. And prove to you why this is useful to learn. All right, so I'll do the first 4 again. Now we're looking for which set. All right, set rather than line itself. So it's address, if it's just 1 byte each, so it's address divided by 1 mod 4. So address mod 4. All right. So if we want to read address 12, that's going to set 0, and we have 2 options. We're missing, of course. We missed. But that's going there. 10, 10, 10. So that's being placed. Let's just place it here. So address 12 is going there. Then 17, 4, 8, 12, 16. So that's going to set 1. It's in neither of these. So we're going to place, 12 here. And going either of them. They're both empty. So let's just place it in line 0. Then 3 is, of course, going to go to set 3. We'll place it in line 0 again. And then 12 again, we hit. We hit. It's there. Cool. We keep track of that. All right. Did we hit? Did we miss? So, all right, you try the rest. You're going to evict the least recently used one. All right, so the first thing you got to figure out is like which sets are these going to go to? So 5 mod 4 is 1, 1 mod 4 is still 1, 4, 8, 12, 13, so 1, 1, 0, 0. So that's where they're going. Now let's figure out what's happening there. So 5 is going to set 1. We're missing, but we have room for it, so we'll place it there. So placing the 5 there. And then we have 1 going to 1. oh no, we've run out of room, so we have to evict somebody. The least recently used one was definitely the 17 because we just put the 5 there. So we're going to kick out the 17 and put the 1 in. So now it's holding in each of these sets address 1 and address 5. All right. And now a 13 comes along. It's like, okay, 13, you're also going to set 1, and we got to kick somebody out again. Darn. So it's 5 versus 1. Who's the least recently used one? It was the 5, right? Because that was older. Placed in older. So we're going to replace the 5 with the 13. And then finally we hit. We get a hit with the 13. Great. And then we read address 4, which does not exist. It would go to line set 0. We have some room in line 1. It's empty right now, so we'll place the 4 there. And then we read 12, which hits. It missed last time, didn't it? So I only had to do 2 evictions for these guys versus the 1, 2, 3, 4 evictions for the same addresses with the direct mapped cache. So this is better. Isn't that nice? All right, so I promise that there's a third. This is just like a philosophical kind. Nobody puts this in an actual CPU, but if you just had one big set, that's called a fully associative cache, and any block could go anywhere. Just like have to do like a linear search through all of them. So it's just not useful. It's too big to be useful, but let's pretend we had it. Let me show you what it would look like. It's just a thought experiment. This is like the best possible cache. So you want to compare your caches that you make in real life to this impossible cache that's like as good as it could possibly be with LRU replacement, all right? It's a fully associative cache. If we could make one of these, we would. Let me show you why, all right? So let's say we're going to read all these addresses in that order, and the block size is 16 bytes each. And so they're all going to set 0, right? It's just mod 1. It's always set 0. They can go in any of these lines, all right? So you kind of have to do a linear search through all your lines when you're looking for something, which is prohibitively slow, and so we don't do that. But this is like as good of a cache as you could possibly have. So you want to compare your real ones that you make to this one, all right? So you read FA, it could go anywhere. It could go anywhere, so let's just place it in line 0. 3.7 can go anywhere. Let's place it in line 1. Try to keep everything as much as I can. 3.7. 4B misses, but we can place it there. FA, I can place it there. Oh, sorry, it's a hit. FA is a hit. It's already there, okay? And then we'll say that our block sizes are 16 bytes. So this is really F0 through FF. This is really 3.0 through 3F, all right? So then we read what? 4C, another hit. Cool. 7B, it's not there, so we'll load it in. The entire line, the entire block, we'll load it. Then BA, it's not there. We'll load it. We got room. BA, then 13B, well, it's not there, but we got room. We can place it in any of these. And so do you see how there are no evictions with this kind of cache? There will be as we read more than just like 8 different addresses, but we hit every time we could possibly hit with this kind of cache. So this is like the pie-in-the-sky dream of a cache. We can never really implement one in hardware, but this is what you compare your other implementations to. All right? So yeah. Let's go back to just the breakdown of caches, because I told you just for a second, there are 2 different L1 caches. We need to explain that, all right, further. So there are 2 different kinds of caches for L1 because your program needs to read both data and code, right? Code and data. You got your global memory, the stack variables, the heap, that's all going in data memory. And then your code goes in like the text section. Remember that? .text. .text versus .data. They're both living in your program somewhere. Like here's your text section. You still have like, you have the byte encodings, right, of like your move instructions. Move W1 into W0, whatever. Then your data section is similar. You have memory, and it's like you're storing the data value 42, the int 42 replacing with 43, whatever. So your text section, first of all, is not editable, so that's worth having a different kind of cache. And then also, it's storing different. It's read-only essentially. It's not editable, and you're using it differently than you're accessing data. So it's nice to have 2 different caches at the L1 level: an L1 data cache and an L1 instruction cache. All right. So text is its own segment of memory. It might be clobbering your data, which might like be making you use like go to memory more often than you need to. All right. So we'll have 2 L1 caches, one for just instructions and one for just data. Instruction caches are kind of cheaper to make because you only have to read data ever. You're never writing to like changing the value in an instruction cache, which kind of ruins things. But data caches have to be written to, and so then you have to play a weird game. So let's say you change the value, like in your data section, you're reading an address, you write to an address, it was 42, now it's 43. So you just had this memory, it was in your L1 cache because you wrote to it, it was there, you changed it, its value, you changed it there. That causes a problem for every other program if you don't propagate that change to everybody else, okay? You have to write back those changes. So like you just changed, this is one strategy at least, you just changed that value in memory here. You need to tell the L2 cache about it, you need to tell the L3 cache about it, and you also need to tell main memory about it. Because somebody else, right, somebody on a different core might be trying to read the value, and if you didn't change it here, it would see the old version, and that's not okay. You want to make sure everybody's up to date. So your data caches need to be writing back to memory. And that takes some time. Hopefully you can just let it happen and go on with your further instruction executions, but that's something that's different than the instruction cache has to worry about. So yeah, to minimize evictions as well as like make it cheaper in a way, because you have to only write back to data stuff, you're going to have two different caches at the lowest level. Okay, so that's instruction cache versus data cache. I hope that makes sense and why you would want those. And then finally, let's talk about another hardware vulnerability. This is unfortunate. All right, so this is back in 2018. A bunch of CPUs were affected, and it's called meltdown. You go look that up on Wikipedia if you're interested. What it did is somebody who had access to who was able to write a program, they were able to read any memory address in the computer, including memory addresses that belong to the operating system, which are supposed to be protected, including addresses of programs that are currently running that are not that particular program. So that's insane, right? That's insane. You're able to read memory that's not yours, which might hold passwords, might hold like security keys and things like that. So it was a combination of pipelining, which we know about, plus caching, which we just learned. All right. So the idea here, the reason this was an exploitable thing was that a lot of pipelines, right, you're trying to run, you see like you're working on like the write back over here and you're doing the fetch over here or whatever. And like you're trying to figure out like trying to get ready for the next instruction after that even. So many pipelines, they're loading memory before they check and see if that address is supposed to be accessed. So I was like, all right, you have a write instruction, like I'm getting ready to run this instruction right here. Like this is where the memory happens, but I'm not actually sure if I have access to it. So like in the fetch, decode, execute stage on this instruction, let's say, like you're getting ready to load this memory, but you're not actually sure if it belongs to you. Okay, so like that's further along in the pipeline, if that makes sense. And so it just gets speculatively loaded by the CPU. It's like, all right, I don't know if you get that yet, but we're just going to try to load it right now, and we'll see what happens. And so it does, and that memory gets temporarily loaded. And because of that, it's being placed in at least one cache. All right? And so you can steal it from the cache by having to by doing some fancy stuff that's like beyond the scope of this class, but you can steal it in a certain way from the cache, and that lets you like branch based on some code that didn't belong to you, some memory that didn't belong to you, which is fun to think about. So yeah, we love pipelining and we love caching, but it also can break down, and in some security heavy fields, you might want to disable those things. Something, food for thought, right? Something to think about. So yeah, the rest of the time is yours to do your lab, but I do want to give you some hints on your most recent lab. All right, so like you are being forced to load an opcode, for example. Like here are what your instructions look like. It's 32 bits per instruction, right? And your opcode is right here. Opcode. It's like you want to get out this bits and then also only look in the rightmost 4 bits of that even. All right, so how do you get these bits only? How do you do that? All right, because each instruction, remember, is one 32-bit integer. So you're going to have to do bitwise stuff, and let me give you an example. All right, one 32-bit int. So let's have it a silly example. Let's say that we want to get bits 5 through 7 out only of a number. Let's see how we can do that. So here is int x equals 42, and 42 in byte form, if I remember. It's just alternating ones and zeros. That's helpful for me. Cool. So like here's the number x. It's an int, and so it looks like this in memory, right? It's in binary. It looks like this when you place it in a register, for example. 0, 0, 0, 0, a bunch of zeros, zero padded until you get to the end. It's a bunch of ones and zeros alternating. So it looks like that, like that, like that, but a bunch more zeros. All right. So that's what it looks like. And I think I wanted to output, I want to extract bits 5 through 7 of this number. So which are bits 5 through 7, first of all? This is bit 0. This is bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7. So I want to pull out these guys. All right. So let's figure out how to do it. Here's the secret. We want to get these over to the rightmost side. And so I want to shift away these guys, these 5 bits. So what I'll do is I'll take x and I'll right shift it by 5 to get the rightmost thing that I care about over at this bit number 0. All right? Do you see what will happen there? That's going to force this number to become a bunch of zeros and then 0, 0, 1. Now what I want is in the rightmost 3 bits. So that's good. That's what I care about. And now I want to extract those rightmost 3 bits because there might be other things. There might be ones over here if it's a different number, right? There might be ones. So the way to extract the rightmost 3 bits is to use the bitwise AND operation. Okay, so like, let's say I got a number that looks like this. Like there's my 001 at the end of that or whatever. Sure, something like that. To extract just the rightmost 3 bits, what you do is you AND with ones in those positions and zeros everywhere else. You see that? So that's going to force zeros on all these guys, or 5. And in all of these, it'll take a 1 if it was a 1. It's going to preserve them. All right? Everything else is getting zeroed out. So 0, 0, 1, and there's my answer. Okay? Everything else is being made a 0. So that's the secret. This is the number 7, I guess. But you can just hard code that in C++ with the 0b stuff. So you can say, all right, how do you extract bits 5 through 7? Bring it back. You're going to shift right by 5, by your lowest bit. And then you're going to AND with the number of bits you care about. So like 0b, 3 ones, right? 3 ones for those 3 bits. And then you'll have a number between 0 and I guess 7, and that'll tell you which bits were set. Okay? So that is the secret. That's how you do it. And so that should help as you're extracting stuff. Do yell at me if you have any questions, but I think that's all that I wanted to say for the day. So yeah, I'll see you in the next one.